All right, now I want to do 3 examples for you of how we'll actually use forces in this class. You'll be asked to draw lots of free body diagrams, or you'll be asked to solve mathematical problems where the first thing you need to do is draw a free body diagram. A free body diagram just shows all the forces in a situation. I just added that definition to this slide. So a free body diagram shows all the forces in a situation. And because forces are vectors, the diagram also shows their direction. So consider the physical situation of a pumpkin on a table. Let's draw the forces. The pumpkin on the table will experience the force of gravity, or weight, and then it will experience a normal force from the table, which causes it to not fall down. Now, since the pumpkin is sitting still, that means these forces are balanced. And so what I've done is tried to make each of these vectors the same size. I don't know that I succeeded, but I tried. That shows that the pumpkin is not accelerating. We'll talk more about that later, but just so you know why I'm drawing the arrows, the vectors, the size that I draw them. Those are the 2 forces on the pumpkin. Gravity pulls it down, the table supports it, and so that gets a normal force. Note again, that normal force is perpendicular to the object's resting place, or what the object sits on. There's a right angle between the force I've drawn and the table. Moving on to the next one, also redrawn here for reference. Now consider the physical situation of a book sliding, sliding, that means there's a velocity, on concrete. So this book has a velocity, but that velocity is not a force. Remember that. Velocity is not a force. So the actual forces, there's gravity, or the book's weight, and because that book is not falling down, there is a normal force. And because that book is sliding, or moving, there's something opposing its motion, and that is friction. Now, something you've probably noticed after these 2 examples is that I'm drawing all of the diagrams with a dot. So in a free body diagram, you represent the object with a dot. So no matter how big the object is, you reduce it to a dot. Represent object with a dot. And all the forces on that object must touch the dot. So that's worth writing and saying again. All forces must connect to, must touch the dot. That is a requirement of the AP exam so that the graders know you actually mean for those forces to go with that dot. So if for some reason you wanted to reference the fact that there's a velocity here, you could leave it off of the diagram, see how it doesn't touch the dot, and the grader would know it's not meant to go with the diagram. But to let them know what is meant, you must have all your forces touch the dot. All right, now we have a book sliding down a table at an incline. So this concrete slab is raised up with respect to the ground at some angle. First, we have the force of gravity, which always pulls straight down toward the center of the earth. Force of gravity, and notice I did my dot. Force of gravity. And that book is not falling straight down, it is sliding at some angle with this velocity, and the velocity is not a force, so it's not going to touch my dot. It is going down that ramp, but it's not falling, so there must be some normal force. Remember, the normal force has to make a right angle with the surface. So I have to draw the normal force so that it forms the right angle with the thing the book's sitting on. No, it doesn't have to be exact if you were asked to draw a free body diagram on the AP exam, but it needs to be very close to a right angle. It should be obvious to the person grading it that you intended it to be a right angle. Now, because there's a velocity, there must be friction opposing that velocity because the book is sitting on something. The times when there wouldn't be friction is if like the book were out in space and had a velocity, then there might not be friction. But the book is sitting on something, and there's friction between the book and the table. And that friction is exactly the opposite of the velocity. So opposite direction of the velocity always. Opposite, because it opposes the velocity. And here's a nice pretty one done on the computer for this situation. All right, you need to come in tomorrow being ready to draw lots of free body diagrams, because that's what we're going to do. See you tomorrow.